our world and beyond. Space, in partnership with the European Space Agency.
What really brings us alive is the launch.
I think the most captivating thing is to see the launcher lift off.
Everyone thinks that bit that I did, the part that I made, the screw that I tightened, the software I put in the launcher, will it work or won't it?
Fonctionne-t-il bien ou pas?
It's the crowning moment, and it's really fascinating to see a takeoff.
C'est magique de voir partir un lanceur.
The launch is the crowning moment, the culmination of a long process of careful machining and construction that begins in huge rocket factories like this one. It's here near Paris that the Ariane 5 launcher is hewn from solid aluminium and brought to life piece by piece.
Here you can see the main stage of the Ariane rocket, so the big structure that includes the fuel tank inside, the hydrogen and oxygen, and the propulsion engine for the main stage.
Et le moteur de propulsion, l'étage principal. Plus 20% de charge utile. Alors pourquoi d'aluminium? Et le devant du lanceur. Et on va les mettre sur une barge à la sortie, juste en face du bâtiment.
To give you an idea of scale, the thrust at liftoff of a rocket like Ariane is like the power of 2 units of a nuclear power station, and the turbo pump that feeds the rocket engine has the power of a TGV.
9, 8, 7, 6, 5, 4, 3, 2.
What comes out of the rocket factory is a unique blend of power, scale and engineering skill. Each launch from Kourou in French Guiana is timed to perfection. With just 3 seconds before the engine fires, the last drops of fuel are emptied into the tanks. And at 0, the main stage rocket is fired. 7 seconds later, the Ariane 5 is released for liftoff. Then, there's no going back.
Le point de non-retour.
The point of no return is when we light the solid fuel boosters. A solid fuel stage can't be stopped, so as soon as we've lit them, the launcher takes off.
Le lanceur décolle.
Décollage.
La taille du lanceur.
The launcher is around about 55 meters tall. Its takeoff weight is 775 tons. And typically, the payload, which is taken into orbit, is around 10 tons. So you see the ratio between payload and overall mass that's necessary to take the payload up into geostationary orbit.
Pour emporter cette charge utile vers l'orbite de transfert géostationnaire.
At this point, Ariane's computers are piloting the rocket, carving an arc into orbit. It steers with slight adjustments in the angle of the engine nozzles.
The maximum pivot we can have in these solid fuel boosters is around 6 degrees, but typically, during a launch, the maximum amount of movement is around 1 degree, so that's really very little.
C'est très très faible.
2 étages avec une sous-solide d'acier ou d'aluminium inférieur, l'étage supérieur, l'étage principal qui est ici. Donc un réservoir qui amène l'hydrogène et puis un autre réservoir qui amène l'oxygène. Nous sommes à la jonction.
So we're at the junction between the main stage and the upper stage. A join which you can see is made up of a large amount of recesses and holes in which we put the bolts that hold the 2 stages together, with around 300 fixing points for each stage. So a separation means that basically you cut, so you put a firecracker to cut them apart. We light the firecracker lights a kind of explosive all the way around the stage, and that cuts them apart.
The central structure of Ariane 5 is made from huge sheets of top-grade aluminium. One by one, the panels are machined into shape, with many areas as thin as 2 millimeters thick. Over 90% of the aluminium is removed and recycled, leaving behind the purest and most perfect central part of each panel. They're then carefully bent into shape. Aluminium is used because it can best withstand the extreme low temperatures of the liquid hydrogen and oxygen fuel.
To make a fuel tank, we start with rectangles that are welded together to make a tube. Then we have the two ends, and we weld the rings onto them, and then the rings on top of each other in order to make a perfectly cylindrical fuel tank. Oxygen and hydrogen have the best ratio of thrust to weight, so we find them in a lot of rockets.
The fuel tanks will be covered by an insulating layer to keep the fuel cool. Despite being so thin, these aluminium tubes form the structure of the main stage of the rocket.
The fuel tanks have to be able to withstand the extreme forces of the rocket taking off, so the tank has to be pressurized. It's so thin that mechanically it's not enough, so it's inflated, a bit like a can of Coke if you like, which is rigid because there's pressure inside.
Russian teacher Konstantin Tsiolkovsky is considered the father of modern rocketry. In 1903, he suggested using liquid propellants and expendable stages. After the Second World War, the innovative technology of the V-2 rocket was adopted and adapted by the Americans for their early space program. Then came the first space launch, with Sputnik sent into orbit in 1957 by an ancestor of the Russian Soyuz launcher. The first non-American and non-Russian space rocket was the French Diamant, which launched in 1965. Meanwhile, the Americans developed the heavyweight Saturn V, which would take men to the moon. The 1970s saw the European Ariane project underway, with Ariane 1 blasting off in 1979, Ariane 4 in 1988, and Ariane 5 in 1996. And what unites these machines is that they all work on the same principle to break the ties of gravity.
When you take a balloon and you blow it up and you let it go into space, into the air, the balloon flies away when the air comes out of the hole in the balloon. We call that the phenomenon of reaction. We work on exactly the same principle, a bit more complicated because it's very cold, because there isn't any atmosphere, because we have to take the fuel and the oxidizer with us, but the principle of reaction is the same for a launcher as for an aircraft.
At the moment, there are 3 main European launchers ready to rocket into space. Ariane 5 is the biggest, capable of lifting 10 tons into orbit. Soyuz is the Russian workhorse with a 3-ton payload, while Vega is Europe's new rocket designed to take 1.5-ton satellites into low Earth orbit. However, Ariane is now being treated to a makeover, the Ariane 5ME, or midlife evolution, which will make it more flexible with the dual payload raised to 12 tons.
Ariane 5ME peut tout à fait
Ariane 5ME can have mixed missions between commercial missions and satellite missions. Having improved performance will allow it to have a communication satellite that will drop off quite early in its flight, and then a science mission that will take further into orbit, and which will carry on its mission. That's part of the strategy for this launcher.
Qui derrière continuera sa mission. Ça fait partie aujourd'hui du cahier des charges du lanceur.
That ability to deliver 2 satellites to quite different orbit positions is the main innovation for Ariane 5ME, which will feature a new rocket engine for the upper stage. The central evolution of the design is the development of an upper stage that can be reignited once in space.
The difficult bit is not only to restart the engine, it's also to have a stage which will stay in orbit for several hours, with fluxes of heat when it's in the sun, and then there's another side which will be cold, and in the middle there are cryogenic rocket propellants, which are very cold. And so the difficulty on the technical side is also to preserve a stage that's capable of being reignited.
The rocket engineers who are developing launches in Europe have to keep an eye on customer expectations as they lay out plans for future designs. The launcher market is seeing increasing competition from the Far East and from private companies in the US. Ariane 5's capacity to launch 2 satellites at a time isn't always a plus.
The today market is requiring to be very available when the customers need to be launched. There is no flexibility from the customers to wait until the pairing of satellites is optimized for a given launch.
Looking ahead 10 years, some of the new technology in Ariane 5, such as the reignitable upper stage, will be included in its successor Ariane 6. The European Space Agency sees the evolution as a strategic move to meet the demands of both commercial and science customers.
That's why we are moving now towards Ariane 6. That is a new solution of launch vehicle where we shall launch each time only one payload.
Meanwhile, back on the factory floor, the engineers continue to machine, weld and bolt together an average of 6 or 7 Ariane rockets per year from components brought together from 12 European countries.
Building a rocket takes 3 years, from the raw materials to the launch. Given the dimensions involved, the best way is to transport by sea. All year round, trucks are circulating, ships are circulating, and then obviously 6 or 7 times a year, a ship picks up all the components in order to deliver them to Kourou and ensure the launch afterwards.
A launch which for many will always be a truly captivating sight.